Hello, welcome back to Calculus 2. In this video, we're going to continue exploring this idea that the area under the graph of a velocity function will produce the displacement of the moving object. In other words, if we graph how fast the object is moving and we find the area under that curve, we will discover how far the object has moved. So when I say here revisit example 2, let's quickly jump back to remind ourselves of what that was. In this example, I said, let's start the marble rolling off to the right at 4 feet per second, and we're going to cause it to decelerate at a constant rate. So we're going to slow it down so that its velocity is going down by 1 foot per second every 1 second. And that's what produced this velocity curve that was a straight line with a downward slope of -1. That was that rate of deceleration of 1 foot per second per second. And so then we looked at those two triangular areas, and we found their areas to be 8 positive above the axis and 2 negative below the axis. And so that told us that over these first 6 seconds of travel, the marble moved a total distance of 10 feet, but a net displacement of 6 feet. So in other words, it's like it moved 8 feet to the right, and then it came backwards 2 feet. So it ended up 6 feet away from where it started, but it traveled 10 feet in doing so. Now, in the first example, I showed you that the idea of distance equaling rate times time, that applies when the velocity is constant. And I said, well, we're going to have to come back to explore why that works when the velocity is changing, when it's not constant. And so let's do that with this example number 2 here. So we have this velocity function that's a y-intercept of 4 and a slope of -1. There's that same downward sloping line I was just showing you in that example. And we have it on the domain, just for now, let's focus on 0 to 4. Let's forget about that blip that went under the axis. I want to focus on just the positive area first, just to make it a little simpler to discuss. Let's discover the displacement of the marble over just those first 4 seconds. So remember, based on what we discovered earlier, we should end up with 8. We're just looking at the positive area there. So we should end up with 8. Here's what we're going to do. Now, I know this is incorrect, but pretend that the speed was constant on those first 4 seconds. Let's say, just as a really rough, honestly terrible estimate, let's pretend that that 4 foot per second speed at the beginning, that stayed constant. What would the area under that graph be? Well, if it was really that just constant flat speed of 4 feet per second over the span of 4 seconds, that would give me a nice big square, and I'd have a net area of 16. Now, like I said, that's a terrible estimate. And in fact, we can say it's an overestimate because that horizontal line up there goes above the graph that we want it to be at all moments in time. So this is definitely way too big, and that's what I mean by an overestimate. So let's think about how we can make that estimate better. Instead of pretending the speed is constant for the entire 4 seconds, let's break up that 4-second time frame into 2 equal-sized pieces. Let's break it up into 0 to 2 seconds, and then 2 to 4 seconds. And let's pretend that the speed is constant on each of those smaller 2-second subintervals. So let's pretend that the speed is starting at 4 and it stays at 4 for the first 2 seconds. And we'll find the area of that tall rectangle. That's going to be 2 times 4, that's going to be 8. And then let's pretend that over the next 2 seconds, the speed is constant, and we're going to use the height of the actual function. Remember that the actual velocity curve is this line here. And so for the 2 to 4 second subinterval, let's pretend that the speed is what it actually is at 2 seconds. So here, f of 2 is actually 2. And that's what I'm going to use as the height, 2, for the second 2 seconds there. And so I'll get an area of 2 times 2, that's going to be 4. And so I end up with a total area of 12. Now that's also an overestimate. I can see that those rectangular areas go above where they're supposed to go. So I know this number is too big, but it's not nearly as much of an overestimate as this one was. That was way too big. And look, we've now cut out this square up here that we did calculate in over here. So it's still an overestimate. It's too big because of these regions, but it's not too much of an overestimate as it was earlier. And remember all along that we know that we're supposed to be getting 8 as the correct answer here. So what we've done there is pretty much the main idea for Riemann sums, or approximating areas under curves using rectangular, nicely shaped regions. Here we've done one rectangle, and then we've done 2 rectangles, and that's kind of the main idea. After that, it's just about breaking it up into more and more and more rectangles. So what I have here, instead of trying to draw this for you, is I've used a graphing tool called Desmos, which I highly recommend, to graph this same idea for larger and larger numbers of rectangles. So when you see a little n here, we're going to use that to mean n for number, how many rectangles we're using. And another way to think of that is it represents how many little subintervals of time that we're dividing the x-axis into. So for example, down here when I see n equals 4, I have divided the horizontal axis into 4 equal-sized pieces. And I have used the height of the curve at each one of those corresponding spots. And that will tell me the height of the corresponding rectangle that I'm going to calculate the area of. As another example over here, if I had n equals 8 rectangles instead, well, you can see I've subdivided this time interval down here into 8 pieces, and so I have 8 different heights of the rectangles to use. On each one of those little time subintervals, we're going to pretend the speed is temporarily constant. And so in terms of the graph, what that means is we're using the actual height of the function and pretending it's constant just for a moment. So we're going to calculate the area using that height of the curve as the height of the rectangle. So first of all, that just makes it easy to find the area. I know how to find the area of a rectangle. It's base times height. But how do I find the area of some more complicated region? Well, I'm not quite sure, but rectangles are really nice and easy. But another reason for doing that is to go back to that idea that I said earlier, which is rate times time equals distance. That really only applies when the velocity really is constant. So that's why it's convenient in these examples over here to momentarily pretend that the speed is constant. So I get to use that idea of rate times time. And because that's what I'm doing down here when I find the area of this rectangle right here, I'm using rate, the height, the velocity, that's the rate of change of the position. And then time is the horizontal width, that 1 second of time down here, that's time, and the height of velocity, that's rate. And so their product, the area of that rectangle, is the displacement of the marble, the object that's moving, over that 1 second. And so I'll save us the trouble of doing all these calculations, but you could set this up yourself and use a calculator, or set up some kind of spreadsheet to automate the calculations for you. And what I'm showing you is that as I increase the number of rectangles, and notice that I'm doubling it each time, so 4 to 8 to 16 to 32, you can think of that as every time I have a figure like one of them, the next one I can get by cutting each rectangle in half perfectly and using the heights there. So from 4 to 8, I've cut it in half, 8 to 16, and so on. And notice that the total, when you see A, that's the total area of all the rectangles. That is decreasing, getting smaller. That should kind of make sense because remember that in the first one, when n was 1, it was a big overestimate. And then in the second estimate, when n was 2, it was still a big overestimate, but not quite as big. We cut out some area here that was factored in when n was 1, but not when n was 2. So it's still an overestimate, but it's a better estimate. It's a smaller total. And that's why we see all of these numbers decreasing. But they don't decrease by as much. Notice that this went down by 1, and then went down by a half, and then it went down by a quarter. There's an interesting pattern there. And if you were to set up a nice algebraic expression for this and take a limit, it would turn out that the area it's approaching really is exactly 8, which is what we knew it was supposed to be all along. I have a triangle that's 4 by 4, and so the area of the rectangle is 16, half of that is 8. That's exactly what we were supposed to get. So if you're watching this at home, what I just gave you is an introduction to the kind of the main idea of what Riemann sums are. But what I'm about to say on this slide applies for me as an instructor for my particular students in my course, and it may not apply to you if you're watching this from some other context. But this idea of approximating the area under a curve by adding up area of rectangles, that's called a Riemann sum, named after a German mathematician from the 19th century named Bernhard Riemann. One of the greatest mathematicians in history. And we were really technically just doing what's called left-hand approximations, in the sense that for each rectangle, we were looking at the left-hand side and going up to the height of the curve at that point, and that was telling us the height of each rectangle. So for example, let's zoom in down here. When I see this first rectangle right here, the height is based on the value at x equals 0, not at x equals 1. I'm looking on the left-hand side, and that's telling me how tall the rectangle is. And then for the next one, the height is based on the value of the function on the left-hand side, and so on and so on. We could have done this all along by using right-hand endpoints. Or we could have found the left and the right-hand endpoints and then taken their average to do some kind of midpoint thing. These are all legitimate things that are done. You could even make trapezoids out of these shapes. You can do more intricate stuff like parabolas. I believe that's something called Simpson's rule, if you look that up. These are all things that can be done. So again, for me as an instructor and the students in my course, I am honestly not super interested in our ability to set up complicated algebraic expressions like this and use formal notation. I am much more interested in our ability to understand conceptually what this is doing and what it represents in terms of calculating areas and approximating areas. But we're not going to be doing a whole lot of complicated algebraic manipulations with these things. But if you're watching this in another course, maybe you will be expected to do some things like that. But really, in general, what I want you to get out of this is that what we're finding is a total change from a rate of change. So we had the graph of a velocity function, which is the rate of change of the marble's location of its position. And from that rate, we're finding the area under the curve. We're calculating a total change in position, change in location, and that's exactly what displacement is. So I want you to pick up this key idea that finding the area under some rate of change will tell you overall the total amount of change. The other thing I want you to pick up from this is a major theme of calculus, which is to take a hard problem, to break it up into a bunch of smaller pieces, and then try to stitch them together in some way. Or to take some limit of some kind, to do some kind of infinite process. Very similarly to how when you find, for example, the slope of a tangent line, that's a hard problem, but you break it up into a smaller problem, which is easier to solve, which is finding the slope between 2 points. And that's what a secant line is. And then you take a limit as the second point approaches the first one, and that gives you the answer to your tangent line question. We're doing something similar here in the sense that we're taking a hard problem, find the area under this curve, and we're breaking it up into a bunch of smaller problems, which are find the area of a rectangle. And those are much easier to solve, and then we just have to think carefully about how to stitch all of those areas together and how to use that to approximate the actual problem we're trying to solve. And one thing I'm going to do in the next video is show you how to use some technology to, okay, do some kind of algebraic manipulations and some calculating, but to pass off some work to technology to do the calculations for us. I'll also just mention that if you're going into some scientific field, you might have to be doing something like this, but without necessarily having a, where did that go? Having some kind of formula for the function. So here I had some explicit formula for the function all along so that I could graph it and look at it and talk about it. But if you're in some scientific experiment, maybe you only have discrete data points, and you need to calculate the area under a curve using just those points. And maybe you don't necessarily have a whole curve that's the graph of a particular function formula. But you might still need to do something like this. And I'll just mention this really interesting situation where in the early 90s, somebody had to do that. They needed to find the area under a curve because it represented something in their context. And they essentially rediscovered a centuries-old idea from calculus and published a paper about it claiming that they had invented this thing. And they very well may have, independently come up with the idea. But the idea itself was very, very old, literally hundreds of years old. And so I think it really behooves you as scientists to be aware of mathematical results and theorems and techniques so that you aren't reinventing any wheels and doing more work than you need to, like what happened in this situation. All right, so in the next video, I'm going to show you an example of how to apply these ideas, and we're going to use Wolfram alpha to do some calculations for us. I'll see you there.